Okay, welcome back, Rem. So today we're going to be discussing operations on Dedekind cuts, and namely we're going to be discussing, well, just the basic ones. So addition of two Dedekind cuts and um, the inverse of a Dedekind cut, so the additive inverse, I should say. So essentially what we're going to do is we're going to show that we're going to define addition of Dedekind cuts, which again we want to develop the fact that um, Dedekind cuts and real numbers are synonyms. So that's what we're trying to get to by showing these properties of these Dedekind cuts and making sure they align with our desired axioms. So yeah, so first let's define a plus. So given any a b, just subset of q, and also their Dedekind cuts and a b are cuts. Then we define a plus b, so a plus b to be a plus b, little b, such that a is in a and b is in b. So that's pretty basic, right? That's very intuitive. That's what we expected. And now we want to show that this is actually a cut. If this wasn't a cut, then, well, the sum of two Dedekind cuts wouldn't be well defined with this definition. So let's check. Well, first we should check that the sum is actually, you know, first we should check that it's the first property. So number one, well, it's clearly non-empty since there exists, uh, let's say, um, so there exists A1 and A and B1 and B. By the fact that A and B are Dedekind cuts, they're non-empty. Um, so A1 plus B1 exists. Okay, so, and therefore A1 plus B1 is in A plus B. So call this C1. So C1 is in A plus B. Okay, and now, well, it's also pretty easy to see that A plus B is not, the entirety of Q, and, well, that follows from the fact that both A and B are, they don't take up the entirety of Q by the fact that they're Dedekind cuts. So, and therefore, clearly, the sum of all of their terms will surely, well, maybe another way to say this is that there exists an element in that's not in A. So for all A, call that let's say Z1. Okay, well, let me just write this out. So for all A in A, there exists some, uh, again, I guess I'm going to call it Z1. Yeah, Z1, that's actually, so we saw that, actually, I'm not 100% sure if I proved this. Maybe I'll actually prove this on the side, because it's a really simple thing to prove, but the claim, um, if, so A is, we're going to say A is a Dedekind cut here. If Z is not in A, which is a Dedekind cut, right, then Z is an upper bound for A. And just quick proof. Well, by way of contradiction, suppose Z is not an upper bound for A. Z is not an upper bound well, then this quickly follows that if it's not an upper bound for A, then there exists some, let's call it, I don't know, there exists some Z prime in A such that when we're using the definition of a Dedekind cut, such that Z prime is greater than Z. But that's a contradiction because, well, we assumed that Z was not in A. But this assumes that Z is in A by definition of a Dedekind cut. Because by the third property, anything less than something in a Dedekind cut is going to be in the Dedekind cut. Okay, so I think that's pretty simple. So there exists here, let's continue here, there exists Z1, I'll just say Z for simplicity, Z1, yeah, Z1 that's not in A, such that Z1, I guess, yeah, I'll just say Z1 is I'll just abbreviate it upper bound. And then similarly for all B and B, there exists Z2 not in B. So maybe Z2 is an upper bound for B. So in other words, it just holds that. Following from here, we have this, and then this. So just add them together. Get A plus B is less than Z1 plus Z2. Okay, well, then it holds that, well, we surely have an element. We just found an element that's not an A plus B, right? It's an upper bound, and therefore it's actually not. You could prove the converse here. I guess to be more rigorous, we would need to prove the converse. But that's pretty easy, right? It basically uses the same method. Again, use a contradiction. Assume it's an upper bound for A. And then, by way of contradiction, suppose that Z is in fact in A, but then there exists some Z prime greater than A, by definition, greater than Z by definition of a Dedekind cut, and that's a contradiction since we assumed it was an upper bound. Okay, so converse is true as well. Okay, so that's the first property done. We need some space, so I might need to actually split this video up into 2 parts because I think this would take this too long. But okay, second property. Well, second property, it's not too bad, right? So, okay. Let's see. So we want to show that given given any element in A plus B, we want to find A prime plus B prime such that a prime plus b prime is strictly greater than a plus b. Well, using a similar method, I'm not going to write down too much notation. We just have a is greater. There exists a prime such that a prime is greater than a. By definition, that a and b are both Dedekind cuts, but then that implies that a plus b, for any a plus b in a plus b, sorry, there exists a prime plus b prime, which is strictly greater than a plus b. So second property checks out. Finally, the third property. This takes a bit more thought, perhaps. Well, take any q. So any q. How should I word this? So we have q less than p, where so p is in a plus b, so we just write p equals a plus b. So we want to show that q is of the form a prime plus b prime, or in other words, it's in a plus b. So that tells us that q is q minus b is less than a. So by definition of the fact that a is the Dedekind cut, q minus b is in a. But since this is an a, we can we just note that q minus b plus b, so an element a plus an element in b, is going to be in a plus b, so the Dedekind, so a plus b, yep, that's it. Well, oh, I just had a strong smell of marker. Well, that just implies that q is in a plus b. So that completes the proof that a plus b is a Dedekind cut, right? That's exactly what we wanted to show. Okay, well, I hope you enjoyed the video, and I'll see you shortly in the next part of this video, where we define negative a, where a is a Dedekind cut, and we show that that is also a Dedekind cut. And actually, after that, we're going to prove the law of trichotomy, if that's how you pronounce it. Trichotomy, I don't know. I always forget it. But it's a very simple fact, and it's just tells us that given any two real numbers, in this case Dedekind cuts, we want to show that either a is less than b, b is less than a. So given any a, b are real numbers, either a is less than b, b is less than a, or they're equal. So that's the law of trichotomy. And I think that's a pretty nice proof. So I'll see you then.